Okay, so let's get started. Okay, so in the previous class, so we learned about the branch instructions, and then we learned that there are two types of branch instructions, right? Conditional branches and unconditional branches. Okay, so we learned about these four conditional branches and then the four unconditional branches. Okay, so actually, in our code, we frequently find uh, if the conditional statement like if else and iterative loop such as while and for loop. Okay, and then in order to implement these statement, we require conditional branch. We require branch instructions, right? So you can just or memorize the definition of these conditional branches and then unconditional branches. So these branch instructions change program counter, right? So it is because using program counter, a processor identify which instructions will be executed, right? So if we just change program counter value, then we can also specify which instructions will be executed, right? So branch instructions just change program count values. Okay. So also the basic block. So you need to memorize. Okay. So it's just the definition. So you need to memorize the definition of basic blocks, and then I explained why basic blocks. The concept of a basic block is important for the compile optimization. Okay, so actually, so inside of the basic block, the compilers can change the order of instructions in order to increase the performance, right? But so between these basic blocks, it's very difficult. Okay, so actually, the size of a basic block is critical. It's it's important for the performance of our applications. Also, in the previous class, we briefly learned about the function calls, right? So you need to understand how a function is called, and then when the so you can just understand, so like the function is the also group of instructions, but in order to execute the instructions in this function, then a processor needs to jump to the instructions in the function. So we need to use the jump instructions. But after the function call, and then, you know, in C, so you can find the return statement. So it means that it returns from the function, right? After the function is complete, then it returns from the function, right? So in order to implement this return from the function, then I said that a processor needs to store return point. So this return point is called return address, right? So by changing the program counter value as the return address, so then we can return to the next instruction of this function call. Okay, you need to memorize. You need to understand this mechanism of function call. Okay, so in order to implement this function call and return, then RISC-V supports the JAL. So JAL is used for function calls, and then JALR is used for return. Okay. So you can just understand that if the function is called, then JAL is used. And then if you find return statement in C, then it can be implemented using JALR. Okay. So in this class, so in the today's lecture, so we learned the detailed mechanism of function calls. Okay, so let's see. So this is the simple function call. So inside of the main function, you can find this function call. So simple function is called by the main function, right? So you can find that simple function only includes return, right? It's very simple, right? There is no, only the return statement exists in this simple function. So it's a function call. So this function call is implemented using JAL, right? So as you can see, so after this function call, you can find the A equal B plus C, but this is the add instruction, right? So actually this function call, the calling simple is implemented using JAL. So you can find the RA. And then you can find the target of this jump instruction. Where is the target? Target is here. So simple label is here. Okay. So this is the program counter. The program counter of this translated assembly code. Okay. So you can find that JAL, the program counter of this JAL is the 0000300, right? And then because the main function calls simple, so it execute JAL, RA, and simple. So you can find this target is here. So what is stored in RA? So I mentioned that RA is the RA represent return address. So return address is stored in RA. So actually the RA is the X1, okay? So RA is the ABI name of the RISC-V register. Okay, so actually this is X1. So in this example, the RA stores the PC of JAL plus 4. Okay, so why? So I mentioned that so actually when a function is called, the caller needs to store return address, return point. But you can find that after this function is called, and then if the when this program returns from a function, then it needs to execute the very next instruction, the A equal B plus C. This is the add instruction, right? So RA just stores the PC of the next instruction. Okay, the very next instruction. So y plus 4, it is because in RISC-V, the size of an instruction is 4 byte usually. Okay, so RISC-V also supports the shrink the instruction set, but usually so the size of a normal instruction is 4 byte. So the next instruction, the PC of next instruction is the PC of current instruction plus 4. So PC plus 4, this is 304. 304 is stored in RA and jumps to the simple. Okay, so here's simple. So you can find that simple has only return statement, right? So it will return to the where A equal B plus C. So this is the very next instruction of the function call, right? So in order to return to this one, then a processor needs to change PC as the 0x304, right? The PC of this next instruction. Where is this PC value? This PC value is stored in RA. So we can use the JALR. So it reads a data from RA. So this is the source register, and 0 is the offset. So this means the RA plus 0. Okay, so and then because the RA is storing 0x304, so this is the 0x304. Okay, RA plus 0. Okay, and then using this value is stored in PC, the program counter. Okay, and then 0 is the destination register, but I mentioned that the 0 is always 0. So the so this is not stored. Actually, when the JALR is executed, the PC plus 4. So in this case, this is the 520. 520 needs to be stored in this destination register. But as you can see, destination register, currently the destination register is 0, and then actually the 0 register always has 0 value, right? So it's not updated. Okay, it's not updated. So, but if we use other registers such as the X2, then the PC plus 4 will be stored in the X2, this destination register. But in this case, we use the 0 because the return address doesn't. So the processor does not need to store return address. Okay, so in this case, okay, because so this is the final function. It's a leaf function. Okay, so PC is replaced with this value. So in the processor will execute this instruction. Okay, so this is the function call mechanism. Okay, so try to understand this function call mechanism, right? So I think it's not difficult, right? So the function call. So when a function call is executed, then this is some typical operations, typical conventions. So caller. So if you see the function call, so this is the very simple function. So this simple function does not require any arguments, function arguments. So what are function arguments? So the function arguments are input data to function, right? So actually, so if we use the function call like this, so function actually require arguments, right? So caller, when a function caller calls a function, then the caller needs to pass arguments value. Arguments to callee is a function, okay? So caller needs to pass arguments, right? So when this some function is called by main, so main is a caller, then these value need to be passed to sum. So transferred to sum, right? And then these values are stored in a register A0 to A7. Okay, so you can find, so actually this A represent the argument. Okay, so this is the ABI name, right? So this is ABI name. Okay, and then jumps to callee. Okay, so caller stores arguments to these registers from A0 to A7 and jumps to callee. So this is the function call. And then callee, when a function is called, then callee performs instructions, right? So obviously, and then returns to result to caller. So in this example, the return does not have any arguments here, but in this example, you can find that return just returns A plus B. So this is the result of a function, okay? So actually, usually a function has a return value, right? So this return value is stored in A0. Okay. So using this A0, the A0 is transferred to the caller. Okay. And then returns to the point of call. So using the return address, then it returns to the caller the very next instruction of the function call. Okay, so this is the typical operation of a function call. But when a function call is implemented, then this is important. So actually, let's see this example. So this is the simple function with the arguments, right? So you can find that if of sums uh, receives these 4 arguments from a caller, is a main function, and then so this is the result. It's a return value, and then it performs the this operation, and then it returns the result. So if we just implement this function calls, then we can implement this function calls like this. So as I mentioned, caller, the main function, stores arguments 2, 3, 4, 5, stores arguments to A0 to A3, right? And you can find that function call. So JAL, it calls diff of sum. So then these arguments are transferred to the function, right? And then you can find the this operation, okay, where is the this operation using the add, sub, add. Okay, so the result of this add is stored in the T0, T1, S3, and A0. A0 is the final value. So this is the return value. And then so the final value result is stored in A0, right? And then returns to the caller. Okay. Then what's the problem? So actually, you can understand that the function is just a group of instructions. And then when instructions are executed, then instructions store some data to registers like T0, T1, S3, right? What's the problem? After the function call, so it returns to the caller, but the caller may require the data in these registers like T0, T1, S3. Okay, so you can find, so actually you in this example, I did not show any instruction between this int y and then diff of sum, but you can find this is it's not shown, but there can be many instructions. Okay, and then the operation result, the execution result can be stored in registers in the caller. But what's the problem? When the function is called, then this function override some registers like T0, T1, S3. Okay, and what's the problem? If these values are overwritten, and then a caller cannot use the original value. Okay, so the original values, original data stored by caller can be lost. Okay, so because it's overwritten. So what is required? Temporary space, right? So in order to avoid this overwriting of data, okay, overwrite of data, then we require temporary space, okay, right? So obviously right. Okay. So this data actually temporarily stored in stack. Okay, stack is the some temporary memory when a program is executed. So it's, you can just understand that stack is the temporary space, temporary memory space. So and then as you know, so this is the memory, right? So the the register value can be temporarily stored in stack memory. Okay, so stack exists in main memory, right? So let's see the example. So okay, so uh actually if you see that this code, that you can find that, so you can find the store instruction. Okay, and then in the store instruction, S3, T0, and then T1, the data in these registers are stored using the store word instruction, right? And then function execute add instruction. So it T0, T1, S3 is overwritten by the value computed by functions, right? But the original value exists in memory. So you can find the store instruction. So it means that the the data in S3 exists in memory, and then address is the 8 plus SP. Okay, 8 plus SP address, and then the S3 is stored, the value of S3. So, and then, the function completes its operation, then it restores the values from memory. So that's how the processor uses temporary space to preserve some data from caller. Okay, so in order to preserve original data from caller, then a function can store register values to the memory, temporary memory, and then this temporary memory is called stack. Okay, it's called the stack space. Okay, then let's see what stack is. So what is stack? What is the meaning of a stack? Okay, so stack is just like the some stack of some object, right? So stack is just a stack, right? It's the, so think about the stack of dishes, right? So we have many dishes, and then so we just stack the dishes like this, right? Then how can we use these dishes? And then in order to use a single dish, then we just use the top of this stack. Okay, we just select the top dishes, right? Top dish, and then we use this dish. But when we just stack the many dishes, then actually we firstly place this oldest dish on the bottom of the stack, right? So this is the oldest value. Okay, so so you can just understand that the stack is the last in, first out queue. Okay, so it's called the LIFO. So last in, first out. Okay, so last in, so it's lastly placed dish is firstly out. Obviously, right? So because think about the stack of dishes. So stack memory is managed by like this stack of dishes. Okay, so last in, first out queue. So let's see the example. So this is the stack memory. So it's a stack memory space, and then a single data is stored in the memory space 1. Okay, it's a 1, and then new data is new data is received. So new data arrives, then this new data, the data number 2, is just stored on the top of the stack. Okay, so you can find that after that, the stack includes the data 1 and data 2, but you can find that data 1 is located in the bottom of the stack, and then data 2, it's a last data. The last data is located in the top of the stack, obviously, right? Because think about the stack of dishes. And then new data comes, and then new data comes, and then new data stored in the top of the stack. So if you can find this data structure, so it's a queue, and then after that, the 6 is here. Then the data structure is organized like this. But you can find that on the top of the stack, the last data, the data 6 is located on the top of the stack. Okay, and then after that, we can just use the data in the stack. Okay, so and then so which means that we can just remove the data from this stack space because this data is not required. So in this case, we can just remove the data from the stack, but in this case, the data on the top of the stack is removed first. Okay, so this called the hop, and then this operation, the data comes to the stack. So this operation is called push. Okay, if data is pushed, then it's built on the top of the stack. And then if the data is pop, then the data on the top of the stack is removed. Okay, it's a push. So in this case, so you can find that 6 is removed first, and then 5, 4, 3, 2. So this is the operation is called pop. Okay, the stack memory is managed like this. So it's because when a function is called, then this data is temporarily stored in the function. Okay, and then we can just manage this temporary data like the stack. So last in, first out queue. Okay, and then so in order to access the data in stack, then we need to identify address, right? So in order to access the data in memory, then we need to identify address, the address of data. So stack is the same. So I mentioned that stack exists in main memory, right? So stack is the temporary space, but stack exists in main memory. So when a program manages a stack space, then it uses stack pointer. It's called the SP. Okay. So if you learn the C, then I believe you learned about the concept of pointers. And then I also explained that you can just understand that pointer is the address of data. So it's a stack pointer. So stack pointer just points the address of the top of stack. Okay, so this is the stack pointer. And then by adjusting this stack pointer, then stack memory space is managed. So this is the example. So this is the address. So this is the stack space, and then stack pointer is pointing this address. Okay, and then using this stack pointer, then we can just access the data in the stack memory. So in this case, if we just use the SP plus 0, then it points the address of this data. So you can, what is the address? The address is BEFFFAE8, right? And then we want to increase the stack. What? Because we want store more temporary data in the stack. So in this case, then we need to adjust this stack pointer. It is because stack pointer is just points the top of stack. And then actually in a program, in a computer program, the stack is increased to the down. So down of address. So it goes down. When the stack is actually point this top of this temporal space. And then if the stack space is increased, so because the processor needs to store more temporary data in the stack, then we need to adjust actually a processor needs to adjust the stack pointer. So in this case, then the stack pointer goes down. Okay, so stack starts from so this is the address map, and then address value 0 to FFF. Then usually stack starts from nearly top of the maximum value of the address, nearly, because some space is reserved for operating system, right? So, and then when a program increases a stack space, then it adjusts the stack pointer to the down of the address. Okay, so it decreased the stack pointer. So in this case, a program wants to store the two data to what's this data? This is the 4 byte for 832, the 32 byte data. Okay, so then as you can see, the stack pointer is decreased. So so stack pointer is changed to the BEFFAE0. So it is like is a SP equal SP minus 8. Okay, then this space is assigned to stack memory, right? And then a program can store temporary data in this additional stack space, like here and here. Okay, so just remember that. So stack is the last in, first out queue in memory. So it's a data structure, right? So so we can just implement a data structure with our application, right? So stack is the data structure in the main memory, but a program uses this data structure as the temporal space. Okay, and stack is managed like this. It starts from the real maximum value of the address space, and then when a stack is increased, then stack pointer is adjusted, but stack pointer goes down. Okay. Okay, let's see the example. So this is the example. So in this case, so I mentioned that in this example, then the function, the diff of sums, may override these register values, but we need to avoid this case, right? You need to avoid this situation. So as I explained, the original data of these registers need to be stored in stack, okay? Like this. So inside of the diff of sum code, you can find these additional instructions, okay? So the first what is the first instruction? The first instruction is add I, SP, SP minus 12. So what does that mean? It represent SP is the stack pointer, and then SP minus 12. So what does that mean? When a diff of sums is called, then it increases stack memory space. How much? By address 12. So it is 3 words, right? It's a 12 byte. Okay, it increased the stack space as by 12 byte. Okay, And then inside of the stack, then it stores the original value. So it's a original stack, and then stack is increased, so stack is decreased by 12. So stack is here, and then this is SP, and then SP4, SP plus 8, and then like this. Okay, so these memory space are allocated in stack memory. Okay, and then as you can see, T0 is stored in the SP plus 0, right? So T0 is stored in SP. So SP is the address. So you can just understand that pointer is the address. Okay, and then the T1. So it was T1, and then this is T0, and then this is S3. Okay, then diff of sum performs their each operation, its own operation, and then it is complete. So the final value is stored in A0. Okay, so this is the return value of a function, and after that, it restores the original data. And where are original data? Original data exists in stack. So it reads data from stack memory using the SP plus 8. So is SP, the S3, the original S3 is stored in SP plus 8. Okay, so from SP plus 8, it reads data, and then it stores data to S3 using the load word. Okay, it's a load instruction. And then T0, so it goes to S3, and it goes to T0, and then it goes to T1. So after the function is complete, then the original data in S3, T0, and T1 are all restored. Okay, and after that, SP is adjusted, so it performs the SP equal SP plus 12. So it decreased the stack space, right? Because after that, after the function is complete, then this memory space the stack space is not required. It's not required anymore. So it restores stack pointer. Then return to the caller. Okay. So actually, because the function also stores data to its register, then the original data in these registers needs to be stored temporarily in stack. Okay, this is very important. Okay, so this is the conceptual diagram. So originally the stack is here, and then the stack is decreased by 12. Okay, so which means that stack space is increased. Okay, so you can just understand. So stack goes down. So you need to remember that stack pointer goes down when stack space is increased. Okay, so and then T1, T0, S3 is stored, and then after call, then stack pointer is restored. Also, this data is restored to registers. Okay, and then this space are not required anymore. So stack pointer is also restored. So stack space is reduced. The size of stack is reduced. Okay. So then, actually, the RISC-V ISA provides the which register provide some rules. So which means that this rule explains which registers are stored by caller or callee. Okay, so sometimes. So this is just a rule. It's just a rule. So actually, so this rule is provided by RISC-V ISA document, right? And then when a compiler is designed, then compiler designer just write the compiler code based on this rule. So this rule just defines the preserved registers. Okay, so the preserved means that certain registers, certain registers needs to be stored when a function is executed. Okay, so in this example, the S0 and S11 are stored by wholly. So which means that the caller does not require to store these registers when a caller calls a function. It means, so which means this is the main function, and then main function calls a certain function like func. Then, but the main function may store a certain data in this register S0 to S11. But in this case, the some requirement, the requirement of preservation of this register data is is given to the function. So which means if these registers are used by this function, then this function, the callee, needs to store the data in these registers in stack. Okay, so for example, if S0 is used for as some A plus B, then in the function, then this S0 needs to be stored in stack by this function. But if this function uses T0, like you can find the T0 register, then function does not need to store this T0 in stack, because if required, T0 needs to be saved by caller. Okay, so this is just a rule. Okay, so this is just a rule. Okay, so and then so if required, then the caller needs to store these registers. So argument is the same. The argument is also and just to pass the function, the callee. Then if these arguments needs to be preserved, then caller needs to save this function, this data, this register data in stack. Okay, it's just a rule. Okay, so you can so that's why these registers are called the save data, and then these registers are called the temporary data, temporary register. Okay, and then the A0 to A7 is the argument. Okay, so it's just the rule. So you can and then so actually compiler is designed, then compiler also considers these rules. Okay. Okay. So based on these rules, then the register T0 and T1 do not need to be stored in stack, because T0 and T1 are temporary registers, and then a function, so this function does not require to store this data, does not require to preserve these data in stack. Okay, because it just used the temporary register. But as you can see, S3 needs to be stored by, preserved by callee is a function. Okay, so it just stores S3 in stack. Okay, okay, so it means a function does not need to store all register values. So based on this rule, if T0 and T1, actually a function do not need to preserve T0 and T1. If T0 or T1 are required to be preserved, then caller needs to store this data in stack. Okay, but the callee do not require to store this data. Okay, this is just the rule. Okay. Okay, so let's learn about the non-leaf function. So from until this point, we just I just showed the leaf function. So which means that this is the last function. But we frequently use the 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 repeated function calls. So it means that the main function calls another function, the foo1, and then foo1 calls the another function, foo2, and then foo2 calls the another function, foo3. So like this. So these functions, foo1 and foo2, are called non-leaf function because it's not the last function. So what is the leaf, right? What is the leaf in a tree? So you can find that the tree, so it's a root, and then it's a trunk. And you can find there's some branches in a tree, and then in the last point of the branch is the leaves. Okay, leaf. Okay, but non-leaf means that it's not the last function. So this function can call another function. Okay, so it means that, so in this example, so function 1 inside of the function 1, then function 1 calls the function 2. Okay, then what's the problem? So I mentioned that when a function is called, a caller needs to store return point, so return address. But what's the problem? When the JAL is executed, then JAL store return address to RA, like this PC plus 4. And what's the problem? The original value is overwritten. Then the original value is lost. Then when a function 1 is complete, then the return address is missing. Is lost. It's overwritten. So it cannot return to the parent function, like the caller. So what is required? So so we learned about the stack. So we can store we can store data, so data to be preserved in stack, right? Data we can store the data to be preserved in stack. So what is the preserved array? The return address also needs to be preserved. So when a function, this function is the non-leaf function, so which means that this function calls another function, then RA also needs to be stored in stack. So this is the example. So before JAL, this is the another call. The call this JAL calls function 2, right? And then you can find that before this JAL, RA is stored in stack. Right. So for the non-leaf function, then we just also remember that RA, the return address, needs to be preserved in stack memory. So it needs to be stored in stack memory. And then no, function 2, when function 2 is complete, then array is restored from stack. Okay, then it performs the return. So it can return to caller. So you need to also remember that for the non-if function, then stack pointer, the stack address, the return address, return point, return address needs to be preserved in stack. Okay, so this is the example. So you can find that the assembly codes are getting more complex, right? Because you can, so there are many function calls here. So you can find that array is stored in SP plus 8. Okay, then it calls the function 2. So function 2 is called by function 1, F1. And then also when F2 is called, F2 just increase the stack. Okay, so it adjusts the stack pointer, and then it stores some data in stack, and then it returns. The stack is restored and returned. So this is the return. Then after return, then it will return to this point, the very next of the function call, the next instruction of the JAL, right? And then and then F1 just execute some instructions, and then finally it restores RA from stack. Okay, it reads the array data from the stack, and then it stack is also restored, and then the return JALR 0 and 0RA is executed. Okay, so this data is here. So this is the non-if function call example. So just to remember that for the non-if function, the stack pointer needs to be stored. Okay. So this is the example. So it's some figure that represent the contents of the stack memory. Okay. So stack is increased. So it means that the stack address goes down, stack pointer goes down. So adjusted, and then you can find that some data like the argument and array. So you can find that array is stored. And then after call to F2, this is the another function call, right? Then you can find that stack pointer goes down to this point, right? Because it just performs the add I SP minus 4, right? So stack address is increased. Stack space is increased. Then this is restored, and these data are restored from the stack, and then array is also restored. Once when F1 is complete. Okay, just remember this array. If for the non-if function, the return address also needs to be stored in stack, so preserved in stack. Okay, this is the function call summary. So for the caller calls a function, right? So, and if the caller calls a function, then caller needs to save any needed registers. So these registers need to be saved by caller. Okay, array T0, T6, A0, A7. Okay, and then store arguments in A0 to A7. So as I mentioned, the function can receive some arguments, okay, from parent function, is a caller. Then these arguments are stored in A0 to A7, and then call function JAL, RA, call it. Okay. And then after that, the function will return some result. So result value is stored in A0. then caller can use this data in A0. Then after that, if some data are stored in the stack, then restore any saved registers. Okay, this is the caller. Some operations by caller, and then callee. So callee is called, then it adjusts stack pointer, and then save registers in some registers in stack. Okay, from like the S0 to S11. So S represent the saved. So it means that these registers need to be saved by a function. Okay, and then function call execute instructions, and then put result in A0. Okay, this is a return value, and then restore registers because some register values are saved in stack. Then a function needs to restore register values and then return. Okay, these are some operations by callee. Okay. Okay. I hope everyone can understand. Okay, so let's see the recursive function. So actually, what is the recursive function? The recursive function means that a function calls its own function. So function calls recursively its own function. Okay, so recursive function means that a function that calls itself. Okay, and then it recursively calls its own function. Okay, so then let's see how recursive functions can be implemented in RISC-V instructions. Okay, actually we can. So this is the example of a recursive function. It's a factorial. What is the factorial? Factorial is a n. Factorial is the n multiplied by n minus 1 multiplied by n minus 2 blah 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 until n minus 2 n minus 1 multiplied by and until 1. Okay, so we can implement this factorial using the recursive function, right? Like this is the one. This is the factorial, the fact int n. So you know, so this fact function receives argument n. Okay, and then if n is less than or equal to 1, so this is the last condition, right? If the n is 1, okay, then just returns 1. Okay, so because n factorial 1 factorial is 1. Otherwise, return n multiplied by fact n minus 1. Okay, then so you can find that this fact function calls another function, but its own function. So it's like a fact. It calls its own, but what is different? Argument is different. Okay, then how can we implement this function? So sometimes, so actually I don't like this type of function, but sometimes we can implement function like this, right? Recursively calls, and then this is good for some exam problems, right? This is a good example of exam problems, right? So then how can we implement this recursive function? So firstly, we can just translate this recursive function like the normal function. What does that mean? So this is the fact function. So you can find that this is the fact function. Okay, so you can this is fact, and then if n is less than 1, then it returns 1. So which means that we just store 1 in A0. It's a return value. but this is the condition. So by checking the condition, and if the condition is the n is the argument, the input argument is less than or equal to 1, then 1 is stored in A0. How can you implement this? So we need to compare with the 1, right? So we can use the BGT. Okay. Then so we just store temporary data 1 to the T0, and then we just compare input argument with T0. So 1, right? So this T0 has the 1. And then if the condition is true, then goes to else. So so we learned that if condition, we can just implement the it is if condition using the conditional branch is using the opposite condition, right? So for this result is like it's just the store 1 to the A0. This is a return value. Then return. Right. So this part. How about the else? So this is the else part. So this is else. Then we need to adjust the n-1, right? So so A0 becomes the n is n-1, and then go factorial. And then we need to perform the n multiplied by fact n-1. So it performs the n multiplied by factorial n-1. So because it calls the fact here, the result of this fact will be in A0, right? So A0, right? And then also the final result of this return is also needs to be stored in A0. So T1 needs to store some n, the stored argument value. Okay. So problem is that n is overwritten. Okay, in this case. So because we just adjust the argument here, so A0 is adjusted. So the A0 is missing here. A0 is the list is the last. So we need to save n. Okay, n in the temporary space stack, right? So if a certain data needs to be preserved, then we need to store this data in stack. Okay. Also, this function calls another function. It's a non-leaf function. So RA. So return address needs to be stored, right? So if you see this code, so we can know that n argument n needs to be stored, preserved. Also RA also needs to be preserved. Otherwise, and then we can just implement this recursive function like the normal function call. Okay. So by considering stack, okay, then we can write the complete code like this. So I explained that n needs to be stored in this function. It's a fact. And then also RA needs to be stored because RA needs to be preserved. This is because this is the non-leaf function. This function can call another function, but its own fact n-1. Okay, it will call its own function, but in this case, we also need to store return address, right? Because it calls another function, even though this function is its own function. So look, so it adjusts the stack pointer, and then in the stack pointer, we will store n is argument, and then we will store RA. Okay. And then if the For this case, it just returned 1. So it just adjusts the stack. So it restores stack pointer. And then if the else state, then we know that n needs to be stored. So restored from stack. So because the n is already stored in the stack. So JAL, so it adjusts the argument. So it becomes the n minus 1 and it calls the fact function. So then what was then? It calls the fact function. Then it goes to here. Okay. So JEL goes to the here. And then it just store also n in stack and then return address in stack. And then only the argument is adjusted and then it calls the fact function again. And then the return after the return from the fact function, so you can find that T1 restores the n. So by reading so n from T1, n from the stack space, and then this n is stored in T1. And then also return address is restored because we need to go to this function needs to go to the caller, the parent function, but its own function. Okay, then stack is restored, and then it performs this multiplication. So n is restored from the stack, and then it is stored in T1, right? So using the T1 and A0, so this is the result from the function, right? So this is the result from the function. This is the A0 and this is T1. So T1 is multiplied by A0. Then it is also stored in the A0 and then it returns. Okay, this is the return. Okay. So sometimes, so it may be tricky. So it may be tricky, but so try to understand. So so I just shows this step. That is an example of fact 3. Okay. So and also this slide shows the contents of stack memory. So fact 3. So it means that n equal 3, right? And then where is this n? This n is in the A0. So A0 has the n and the 3. Okay. Then the people call the stack pointer is here, and then so fact 3. So fact 3 is called, right? So then A0 is stack pointer is adjusted, right? And then A0 is stored in stack, right? And then the RA is stored. 40분밖에 안 됐는데. Then then this function needs to call fact 2, right? Because the n is larger than 1. So it also stack is adjusted. Then 2, argument 2 is stored in stack, and then return address. The return address again stored in stack because this function also needs to call fact 1, right? So the function call, then 1 is stored, and then return address is stored. And then in this case, so this is finally the argument is 1, then it will execute this part, right? So you can also find the return address. So return address is here. Okay. So and then you can find that when the return is executed, then it the SP is adjusted like this, and then the N is restored from stack memory. So this is N equal 1, N equal 2. So this is stored in the T1, and then it is multiplied recursively. Okay, and then it goes to the return point. Okay, so so if you see this figure, okay, the stack, the diagram of the stack memory, then so I believe you can understand how so this recursive function operates. Okay, so you can find that when the return from this function step by step, then it restores the stored argument value, and then using the stored argument value, the multiplication is performed, and then it goes to the return point again and again. So what is the return point? Return point is here. Okay. So this is the example of a recursive function. It's a factorial. But like this, so so we can start from some normal translation, so like direct translation. So so firstly, we don't need to consider the stack, but and then we can just write the translated code like this, and then also like the normal function call, then it can call its own function, like back here. But we need to remember that when a function calls another function, then required data needs to be stored. Now, what are required data? Return address, and then in this case, n. The argument n needs to be stored. Where those data need to be stored in stack. So stack needs to be managed like this. Okay, and then so you can find that stack memory space. There is a managed like this. Okay, and then after that, so stack is restored, and then it reads the required data from stack, and then it restores stack pointer. Okay, so this is some example of recursive function. So as I mentioned, so actually this is good for so I frequently use this case as some exam problem, exam questions. Okay, so it may be a little bit tricky, but try to understand. Okay, I will stop here. Any questions? Okay, thank you for your attention. See you in the next class. 감사합니다.